In the 21st century, China has emerged as a global leader in infrastructure and engineering, achieving feats that have astonished even the most developed nations. Once plagued by the hardships of the century of humiliation, China has now risen to become an economic and technological powerhouse, transforming its cities and landscapes with massive construction projects. Former U.S. President Donald Trump even acknowledged China's superiority in infrastructure, admitting that America could never compete with China's advanced roads, bridges, and urban development. But is this reputation well-earned? Is China truly surpassing the West in engineering and technological innovation, or is it just an illusion created by grandeur and large-scale projects? To answer this, one of the most groundbreaking projects to examine is the Shenzhen-Zhongshan Link, a massive infrastructure development that features bridges, artificial islands, and one of the world's longest underwater tunnels. This 24-kilometer megastructure is not just a testament to China's ability to construct monumental projects, but also a symbol of its commitment to economic growth, regional integration, and technological advancement. The Shenzhen-Zhongshan Link is a vital part of the Guangdong-Hong Kong-Macau Greater Bay Area, a region that aims to become one of the most important economic hubs in the world. China is home to some of the world's busiest and fastest-growing cities, and Shenzhen is one of its most important economic powerhouses. Often referred to as China's Silicon Valley, Shenzhen is a global leader in technology, finance, and manufacturing, housing some of the biggest companies in the world, such as Huawei, Tencent, DJI, and BYD. It is also home to the Shenzhen Stock Exchange and a booming fintech sector. The city plays a critical role in international trade, with its ports processing massive cargo volumes and serving as an essential link in global supply chains. As a rapidly growing metropolis, Shenzhen requires efficient and modern transportation networks, which is why the Shenzhen-Zhongshan Link is so significant. On the other side of the Pearl River Delta, Zhongshan is an equally vital player in China's industrial landscape. While Shenzhen is known for its high-tech industries, Zhongshan is a key manufacturing and trade hub, specializing in machinery, home appliances, and precision equipment. The city is home to over 30,000 industrial enterprises, many of which are deeply integrated into global supply chains. Zhongshan is also undergoing rapid modernization as part of the Greater Bay Area initiative, attracting new businesses and infrastructure investments. However, the lack of a direct connection between these two economic hubs has been a major challenge. Before the construction of the Shenzhen-Zhongshan Link, the primary travel routes between the two cities included the human bridge or ferries, both of which were heavily congested. The long travel times of 2 to 3 hours created logistical bottlenecks for businesses and daily commuters. The new link cuts this travel time to just 30 minutes, significantly enhancing commerce, reducing transportation costs, and strengthening economic ties within the Greater Bay Area. The sheer scale and complexity of the Shenzhen-Zhongshan Link make it an engineering marvel. The project consists of a 17-kilometer bridge system extending across the Pearl River estuary, featuring 2 massive artificial islands that serve as key transition points. From there, the structure descends into a 6.8-kilometer underwater tunnel, making it one of the longest and most advanced immersed tunnels in the world. What makes this tunnel even more unique is the integration of a submarine interchange, an unprecedented engineering feat that allows vehicles to seamlessly shift routes while underwater. This is the first of its kind in large-scale civil engineering. The construction of the Shenzhen-Zhongshan Link required some of the most advanced engineering solutions ever deployed in infrastructure development. The underwater tunnel is composed of 32 massive prefabricated concrete segments, each weighing over 80,000 tons. These segments were carefully submerged and aligned on the seabed with millimeter precision. To ensure long-term durability, engineers incorporated seismic-resistant technology capable of withstanding extreme environmental conditions, including typhoons, strong tides, and potential earthquakes. Given the frequent geological activity in the Pearl River Delta, this was a crucial consideration. Beyond its structural components, the artificial islands serve multiple purposes. In addition to facilitating the transition between bridges and the underwater tunnel, these islands house essential infrastructure such as emergency response centers, toll stations, and logistics hubs. Sustainability has also been a major focus of the project. To minimize the ecological impact on the Pearl River Delta's fragile marine ecosystem, engineers employed noise reduction materials and environmental protection measures throughout the construction process. The Shenzhen-Zhongshan Link is a testament to China's ability to push the boundaries of engineering, integrating cutting-edge technology, sustainability, and urban planning into a single megastructure. The undersea tunnel, in particular, is a technological breakthrough, redefining the limits of marine engineering and tunnel construction. Stretching 6.8 kilometers beneath the Pearl River estuary and buried at depths of over 40 meters, it stands as one of the most ambitious underwater infrastructure projects ever attempted. Designed with 8 lanes in each direction, it far surpasses the capacity of the Hong Kong-Zhuhai-Macau Tunnel. Building an undersea tunnel of this scale presented enormous challenges, particularly in ensuring airtight connections between segments in a high-pressure underwater environment. Even a minor leak could compromise the tunnel's long-term durability. Engineers tackled this issue by designing precision-machined steel gaskets combined with high-performance elastic sealing materials, ensuring vacuum-tight seals between segments. Each segment, measuring 55 meters in length, 46 meters in width, and 10.6 meters in height, was meticulously aligned using a floating docking system with a 2 mm margin of error, surpassing conventional tunnel construction standards. Another major challenge was ensuring seismic resilience. Since the Pearl River Delta is prone to geological activity, traditional expansion joints were deemed too vulnerable. To address this, engineers introduced highly flexible, seismic-resistant expansion joints that allow the tunnel to absorb and dissipate seismic energy effectively. In addition to structural resilience, the tunnel also incorporates an advanced air purification and ventilation system, featuring HEPA filters and real-time carbon dioxide monitoring sensors. These innovations help maintain air quality inside the tunnel at levels comparable to outdoor conditions. The Shenzhen-Zhongshan Link is more than just a transportation corridor. It is a bold statement of China's engineering ambitions. This project has defied Western skepticism, proving that large-scale, high-tech infrastructure can be built with precision, resilience, and sustainability. By successfully overcoming complex engineering challenges, China has once again demonstrated its ability to execute monumental projects that redefine global infrastructure standards. As the Shenzhen-Zhongshan Link nears completion, it stands as a symbol of the country's ongoing commitment to economic growth, technological progress, and regional connectivity. The Shenzhen-Zhongshan Undersea Tunnel is a marvel of engineering, operating in a seismically active zone. To counteract buoyancy forces, engineers implemented an anti-buoyancy foundation system using a combination of deep-sea anchor piles and ultra-dense reinforced concrete. Given that each submerged segment weighs more than 80,000 tons, keeping them stable without external displacement was critical. Compared to the Hong Kong-Zhuhai-Macau Bridge Undersea Tunnel, where anti-buoyancy was managed with traditional ballast systems, the Shenzhen-Zhongshan Link's approach provides 40% greater stability against shifting seabed conditions. Moreover, the estuary experiences some of China's strongest tidal currents, with speeds reaching 2.5 meters per second. To protect the tunnel from erosion and shifting seabed conditions, engineers used an advanced sediment stabilization system integrating reinforced geotextile layers and dynamically adaptive breakwaters. This ensures that underwater currents do not gradually weaken the tunnel's foundation over time, a common issue in submerged infrastructure projects like the Resund Bridge Tunnel between Denmark and Sweden. What truly sets this tunnel apart, however, is its unprecedented technological sophistication. At its core lies a groundbreaking smart monitoring system integrating 23,000 fiber optic sensors directly into the tunnel's concrete structure. These sensors provide real-time stress, strain, and temperature data, allowing engineers to detect microfractures, monitor load distribution, and predict structural fatigue before it becomes a safety risk. This level of continuous automated health monitoring is a first for undersea tunnel construction and enhances long-term durability by enabling preemptive maintenance before major issues arise. The precision and sensitivity of this monitoring system are unparalleled. The fiber optic sensors embedded within the tunnel boast a 40% higher sensitivity than comparable systems used in the West. This allows for more accurate and immediate data collection, effectively making the concrete think. This feat is so revolutionary that it was recognized by the prestigious journal Nature. The integration of smart sensing technology into traditional concrete structures transforms the tunnel from a static passageway into a self-diagnosing, self-reporting structure, significantly reducing maintenance costs and extending its lifespan. Beyond its sheer scale and technological breakthroughs, the Shenzhen-Zhongshan Undersea Tunnel also sets a new benchmark in environmental protection and human safety. Given the ecological sensitivity of the Pearl River estuary, home to diverse marine life including the endangered Chinese white dolphin, engineers implemented low-noise construction techniques to minimize underwater sound pollution. Instead of conventional pile-driving methods, which produce disruptive shock waves, they used vibration-reducing hydraulic jacks and bubble curtain technology, which absorbs and dissipates noise before it reaches marine species. These measures helped cut underwater noise pollution by up to 60%. They pioneered a steel-concrete composite structure, combining the best of both worlds. The steel shell provided superior tensile strength and flexibility, preventing cracks from propagating through the structure, while the concrete core enhanced compression resistance, ensuring the tunnel could withstand the staggering weight of ocean water above. This combination resulted in a 400% increase in flexural rigidity, meaning the tunnel was 4 times more resistant to bending and deformation compared to conventional designs. This steel shell concrete structure was a complete reimagining of how undersea tunnels are built. Traditional reinforced concrete requires extensive manual labor, making large-scale projects more time-consuming and error-prone. The new steel-concrete hybrid design dramatically reduced labor intensity, allowing prefabricated segments to be built with millimeter precision before being submerged and connected on the seafloor. This breakthrough did more than silence skeptics. It set a new benchmark for tunnel engineering worldwide. By demonstrating that an 8-lane bidirectional undersea tunnel was not only feasible but structurally superior to previous designs, China effectively rewrote the rules of large-scale marine infrastructure. This tunnel doesn't just connect 2 cities. It ushers in a new era of supermassive underwater infrastructure. To get a better sense of how impressive this tunnel is, we need to take a look at the tunnel's precision parameters, precision manufacturing, and assembly. The Shenzhen-Zhongshan Undersea Tunnel is a masterclass in precision manufacturing and automated assembly, pushing the boundaries of what is possible in subsea infrastructure. Traditional tunnel construction often relies heavily on manual labor, but for a project of this magnitude, even microscopic deviations in construction could lead to structural weaknesses over time. To ensure unmatched durability and precision, China implemented an automated production process that surpassed even the most rigorous international engineering standards. At the heart of this operation was a highly automated production line where steel plates were precision-cut and robotically welded with an accuracy level never before achieved in immersed tunnel construction. The welding accuracy of 0.02 mm exceeded the German DIN 6700 standards, one of the world's most stringent quality benchmarks, by an astonishing 22%. This was a major breakthrough, as even a 0.1 mm deviation in tunnel segments could create misalignments that would compromise the structural integrity of the entire tunnel over time. To achieve this ultra-high precision, engineers employed laser-guided cutting systems to ensure millimeter-perfect steel plate dimensions. They also put to use automated robotic welding arms capable of applying consistent, high-strength welds without human error. Real-time AI monitoring systems also detected microscopic inconsistencies, allowing immediate corrections. By eliminating human-induced welding imperfections, this approach dramatically improved the durability of the tunnel, ensuring that it could withstand extreme pressures for decades without significant maintenance. Given the sheer scale of the tunnel, a single continuous structure was impractical. Instead, engineers employed a segmented tube construction method, dividing the tunnel into 22 giant prefabricated segments, each weighing tens of thousands of tons. These segments were meticulously constructed off-site under controlled conditions before being transported and assembled underwater. To ensure flawless integration of these massive tunnel sections, the assembly process relied on gantry cranes capable of lifting and positioning entire tunnel segments with sub-millimeter precision. Automated machinery also ensured that each segment was perfectly aligned before being permanently joined. Moreover, vacuum-sealed alignment systems eliminated even the slightest gaps between segments, reducing structural stress points. Each segment had to be airtight and watertight, as even a hairline fracture could allow seawater infiltration, jeopardizing the entire project. To mitigate this risk, engineers used custom-engineered high-pressure gaskets between tunnel sections, ensuring that the connections were as strong as the tunnel walls themselves. The precision achieved in welding, cutting, and assembly has demonstrated that fully automated, AI-driven megaprojects are not just possible but superior to traditional manual construction methods. In this context, the Shenzhen-Zhongshan Link, a crucial passage connecting Shenzhen to Zhongshan in the Greater Bay Area, offers a glimpse into the next era of engineering innovation. Built to last 100 years, the tunnel is designed to endure severe marine conditions, high hydrostatic pressures, and continuous exposure to corrosive seawater. Achieving such an extended lifespan required groundbreaking innovations in corrosion resistance, structural protection, and self-maintenance. One of the greatest challenges of underwater tunnel construction is the constant exposure to saltwater-induced corrosion, which can weaken metal and concrete over time. To counteract this, engineers developed a 5-layer anti-corrosion coating, drawing inspiration from shark skin, a natural surface known for its resistance to microbial growth, self-cleaning properties, and durability. The tunnel's 5-layer anti-corrosion system is a groundbreaking innovation designed to withstand the harsh marine environment and ensure longevity. At its core, the epoxy resin primer forms the first line of defense, creating an initial waterproof seal that prevents moisture from penetrating the structure. This is followed by a polyurethane barrier layer, which is specifically engineered to absorb mechanical stress and prevent cracks caused by temperature fluctuations. To reinforce the surface against abrasion, high-speed tidal currents, and saltwater erosion, engineers incorporated a ceramic nanocoating, which significantly enhances durability compared to traditional anti-corrosion treatments. Adding another layer of resilience, the hydrophobic fluoropolymer film repels water and oil, mimicking the natural water-shedding properties of shark skin to reduce long-term material degradation. The most advanced component of this system is the self-healing protective membrane, which uses microcapsule technology to autonomously repair minor scratches, microfractures, and surface wear before they expand into structural vulnerabilities. This biomimetic approach ensures that the tunnel remains highly resistant to rust, salt damage, and structural degradation for at least a century. The Shenzhen-Zhongshan Undersea Tunnel is monitored in real time, ensuring that depleted anodes are replaced before they lose effectiveness. This dual-layer protection of chemical coatings and sacrificial anodes ensures that no exposed steel in the tunnel is ever at risk of rusting. Moreover, in any marine environment, underwater structures are prone to biofouling, which is the accumulation of algae, barnacles, and bacteria that can degrade surfaces over time. To combat this, engineers implemented an advanced surface treatment system that provides the tunnel with self-cleaning capabilities. The hydrophobic fluoropolymer layer on the outermost surface prevents organic matter from adhering to the tunnel walls. A low-friction antimicrobial coating disrupts bacterial growth, preventing biofilm formation. On top of this, electrically charged nanocoatings create a subtle repelling force that detains barnacles and algae from attaching. These technologies ensure that the tunnel remains smooth, clean, and free of biological obstructions, preserving not just its appearance but, more importantly, its structural performance and water resistance. Together, these protective mechanisms take longevity to a whole new level. Another area where the Shenzhen-Zhongshan Link pushes the boundaries of practicality is concrete engineering. Using cutting-edge robotics, real-time monitoring, and nanotechnology, the project redefines global standards for undersea infrastructure durability and resilience. Traditional concrete pouring methods are time-consuming and prone to human error, leading to uneven density, microcracks, and structural weaknesses over time. To eliminate these risks, engineers developed a fully automated concrete pouring system utilizing robotic precision and real-time data analysis. Equipped with 1,200 embedded sensors, these robotic systems monitor flow rate and pressure to ensure consistent material distribution, temperature differentials to prevent thermal cracking, and hydration reactions to optimize curing times. This innovation reduces the traditional 90-day manual pouring and curing process to just 28 days, increasing efficiency by 68%, minimizing environmental exposure, and accelerating project timelines. The use of AI-driven monitoring ensures that the concrete is poured at the exact right consistency and temperature, eliminating air pockets and weak points before they form. A common challenge in large-scale concrete structures is achieving full compaction without structural gaps or voids. Conventional techniques rely on mechanical vibration, which can lead to uneven settling and long-term weakness. Instead, engineers introduced a zero manual vibration system utilizing self-compacting concrete, SCC, with nanometer-level flow control. SCC is engineered to be highly fluid yet structurally robust, allowing it to flow into every crevice without external force. Its ultrafine particle composition ensures a 100% seamless bond between segments, reducing the risk of cracks, water seepage, and future deterioration. Moreover, the absence of mechanical vibration eliminates inconsistencies, ensuring that the entire tunnel structure is uniformly strong from the core to the outermost layers. This breakthrough enhances load-bearing capacity, ensuring that the tunnel can withstand immense external pressures, seismic forces, and long-term environmental stresses. A tunnel of this magnitude must endure some of the harshest environmental conditions on Earth, requiring rigorous durability testing beyond conventional engineering standards. The Shenzhen-Zhongshan Link underwent simulated stress tests that measured its resilience against a century of extreme natural disasters. Engineers subjected the tunnel materials to continuous high-velocity water currents and wind pressure simulations replicating the destructive forces of 1,000 Category 5 typhoons. The self-compacting concrete withstood hydrostatic loads without microfractures, proving its ability to survive extreme weather conditions. The tunnel was also tested against Level 9 earthquake simulations, mimicking quakes stronger than those that devastated Fukushima and Sichuan. The high flexural rigidity of the steel-concrete composite ensured that no structural failure occurred, even under severe seismic stress. Additionally, engineers modeled future climate scenarios, exposing the tunnel to conditions mimicking a 3-meter rise in global sea levels. The tunnel's hydrophobic coatings and reinforced water barriers proved highly effective, ensuring it remained watertight under elevated pressures. These stress tests confirmed that the risk of catastrophic failure was reduced by 83%, far exceeding international safety standards and setting a new benchmark for long-term structural resilience in undersea construction. The success of the Shenzhen-Zhongshan Link hinges on China's revolutionary Smart Dream Factory, an AI-driven manufacturing hub, and a massive transport operation that moves 80,000-ton tunnel sections with near-military precision. To meet the immense structural demands of an 8-lane undersea tunnel, engineers turned to a fully automated AI-controlled prefabrication plant, nicknamed the Smart Dream Factory, where each tunnel segment is built with robotic precision. The prefabrication facility behind the Shenzhen-Zhongshan Link operates at an unprecedented level of efficiency, delivering one massive tunnel segment per month. This production rate is 25% faster than previous undersea tunnel projects. This accelerated pace is achieved through a combination of advanced automation, optimized logistics, and precision engineering, ensuring that each segment meets exacting structural standards without compromising quality. Unlike conventional construction sites that are subject to weather fluctuations and environmental variables, these segments are manufactured in a fully climate-controlled environment where temperature and humidity are meticulously regulated. This precision-controlled process eliminates thermal expansion inconsistencies, premature drying, and micro-cracking, which are common issues in traditional concrete construction. By maintaining a uniform curing environment, Engineers ensure that each segment achieves its full compressive strength and structural integrity, reducing the risk of long-term weaknesses that could compromise the tunnel's resilience under high-pressure underwater conditions. The Shenzhen-Zhongshan Link reflects China's ability to merge cutting-edge technology with large-scale logistics to create next-generation infrastructure. The Smart Dream Factory's automated precision, groundbreaking transport system, and rigorous quality control showcase how China is pushing the frontiers of megaproject construction. This project sets a new global benchmark, demonstrating how automation, AI, and high-tech logistics can revolutionize infrastructure development. By setting new standards for efficiency, durability, and scale, China is proving that its infrastructure prowess is unmatched.